Hello students. So up until previous class we concluded our second order ordinary differential equation where we had ordinary points, singular points. We also learnt about basis functions and legendary polynomial. There are other types of special functions, but given the compact content of this particular course we are not looking into them, but of course there are like Chebyshev polynomial, Lagrange polynomial and all that. So today we will start a new chapter. Basically it's a Sturm-Liouville problem. But before we actually look into Sturm-Liouville problem, we have to understand what do we mean by eigenvalues and eigenfunction of a differential equation. We will limit ourselves to second order ordinary differential equations and we will see how do we understand the concept of eigenvalues and eigenfunctions in case of differential equation, right. So let us start. Before we do that, we have to sort of define what do we mean by initial value problem and eigenvalue problem and boundary value problem. So, initial value problem and boundary value problem. So, the formal definition can be of this type, a mathematical problem. So, now we are defining initial value problem IVP and boundary value problem BVP. We are defining these two, right. So, a mathematical problem consists of finding an unknown function satisfying an ordinary differential equation ODE, an ordinary differential equation, and one or more appropriate supplementary conditions, right. Supplementary conditions. The number of these supplementary conditions is normally or usually equal to the order of the differential equation DE of the differential equation. These conditions can be of two types. What are they? Initial conditions and boundary conditions. If initial conditions are given, together with the ODE, then it is called an initial value problem. Then it is called an initial value problem, or in short we can call it as IVP. And if boundary conditions are given, similarly if boundary conditions are given together with the ODE, then you call it as boundary value problem. If both initial and boundary conditions are given, which may happen also, so if both initial and boundary conditions are given, then you can call it an initial boundary value problem or just a boundary value problem, because you have both of them given, right. So, it does not have to be you need to specify if both initial and boundary conditions are given, then there is a separate terminology. Then in that case you can call it as a boundary value problem, because what is important is that the boundary conditions are given, and we can use the terminology as a boundary value problem when both of them are given. If either one of them are given, then you call it as either an initial value problem or a boundary value problem, right. So, similarly you can define BVP. One example could be for initial value problem, suppose we have y double dash plus a1x y dash plus a2x into y equals to 0. This is the given differential equation, and we might be given y at x equals to 0. So, some people write it as y0 equals to alpha, and dy dx at 0 at x equals to 0 as y dash 0 is given as alpha 1, right. So, you do not always have to take 0, you can just say initial point is x0. So, either x at x equals to 0, or you can use y at x equals to x0. So, here I have taken specifically x0 equals to 0 is the starting point, but it does not always have to start from 0, it can start from any x0, and then at y at x equals to x0 you define it as y0 which is alpha, and y dash at x equals to x0 as alpha 1. So, here as you can see you have the order of the differential equation as 2, and you are given 2 initial conditions. So, if you solve this second order ODE, you will be able to determine 2 independent solutions, and when you write down the general solution, it will be a linear combination of these 2 independent solutions. Now, to determine those 2 constants, you require 2 conditions. So, here you have the 2 conditions. So, with the help of which you can be able to determine 2 arbitrary constant, and that will give you the unique solution, the solution that actually satisfies this ordinary differential equation and these 2 initial conditions. Otherwise, when you are solving an ODE, you will get a family of curves or a family of functions which actually satisfies that given differential equation. But when you are given the initial conditions or when you are given the boundary condition, then out of this entire family you are picking up that member of the family which started from y at x equals to x0 equals to alpha, right. So, in that way we have a family of curves, but because of the initial and boundary conditions you are picking out only that particular member which satisfies the initial condition or which satisfies the boundary conditions and the ODE itself. So, this is an example of initial value problem, and another example will be, let us say, y double dash plus a1x y dash plus a2 x y equals to 0, and suppose the problem is valid between the interval x0 to for all x in x0 to x1, right. So, here I will say the supplementary conditions will be a1 y plus a2 dy dx equals to gamma at x equals to x0, that means at one end point. So, if this is the interval x0 and x1, then these are the boundary points x0 and x1. So, at x1 we have this condition, and at x0 we have this condition, at x1 I can have a3 y is equals to gamma 1 at x equals to x1. So, if you have this type of boundary condition, so then in that case we call it Robin boundary condition, right. So, here we have there can be 3 I would say 4 types of boundary conditions in a way. So, if the value of the function is given at the boundary, that means of this type, if the value of the function is given at the boundary, then it is called as Dirichlet boundary condition, right. Let me go to the next page. So, if the value of the function is given, that means y at x equals to, let us say, b, that means the end point is given as y1, then this is a Dirichlet boundary condition. This is Dirichlet boundary condition. If dy dx is given at x equals to b, dy dx equals at x equals to b as, let us say, y2, then this is Neumann boundary condition. Neumann boundary condition. If we have combination of both of them, y plus dy dx at x equals to b, they are both at x equals to b is equals to y3, then this is called as Robin boundary condition. Robin boundary condition. And if if I mean this can be visualized in case of 2D very nicely, that some parts of the boundary. So, suppose if you have a 2D structure and this is the boundary, then some part of the boundary has Neumann boundary condition and some part of the boundary has Dirichlet boundary condition. That means, on this part your dy dx or the flux part is given, and on this part you have the value of the function given. So, basically you have a Dirichlet and a Neumann boundary condition. So, when you have a combination of both of them, we call it as mixed boundary condition, right. So, this is not the mixed one, this is Robin boundary condition, whereas when you have a combination of both Neumann half part of the boundary and Dirichlet at the other part of the boundary, then we call it as so Dirichlet and Neumann, the combination will called as Neumann, this combination will called as mixed boundary condition, right. So, we have Dirichlet, Neumann, Robin, and then mixed boundary condition. So, this mixed one I simply use the terminology because they have a mixture of both the boundary conditions, right. So, now that we have boundary conditions, you can think of that when you are solving an ODE, if you are given initial or boundary condition, then we are determining the solution. Now, how do we relate that solution with the eigenfunction, eigenvalue and then eigenfunction, right. So, suppose if we are given this equation, one example 1, we are given y double dash plus y is equals to 0 in 0 less than x less than L, and suppose y at x equals to 0 is 0 and y at x equals to L is some y1, right. So, we have given this boundary value problem. So, this is a boundary value problem because here we have x running from 0 to L, and at x equals to 0 the value is 0, y is 0, and at x equals to L y is y1. So, this is a nice boundary value problem. When you solve it, from here I can write down the auxiliary equation, and auxiliary equation will be m square plus 1, therefore, the roots will be plus minus I, and the general solution can be written as y is equals to y of x equals to a cos beta x plus b sin beta x, that beta is basically 1. So, I will have a cos x plus b sin x, right. Now, a and b are two arbitrary constants. So, if we try to determine a and b, so y at 0 equals to 0. So, I can substitute x equals to 0. So, y at 0 equals to 0 means what? 0 a cos 0 plus b sin 0. So, b sin 0 is 0. So, b into 0 is 0. So, from here it will imply that a into cos 0, that is 1. So, therefore, we will have a is equals to 0. Now, when y at L is equals to y1, I will have from here y1 equals to a is 0. So, I will have b sin L equals to y1, therefore, b will be y1 by sin L, right. And if I go to the next page, our required general solution will be yx equals to y1 by sin L into sin x. Now, if L is equals to n pi, because we do not know what is our L. So, if L is equals to n pi, then yx will become then, and y1 is equals to 0, and y1 is equals to 0 for then for any b y is equals to b sin x will be the solution, because let us go to the previous slide. So, here we have y1 is equals to b sin L. So, if y1 is 0, suppose at the other end point also y1 is 0, then in that case b sin L pi. So, b has to be non-zero, otherwise the solution will be trivial solution. If you say that y1 is equals to 0, so I will divide by sin L, then you have b is equals to 0, therefore, a is 0, b is 0, so the trivial solution is the only solution, but we are not looking for the trivial solution. So, therefore, I will say b is non-zero, so L must be n pi. So, if L is n pi and y1 is 0, then it can be any b. For any b, this will be a solution, because our equation will always, our solution will always satisfy the given equation. So, is a solution of the boundary value problem, is a solution of the boundary value problem, solution of the boundary value problem or BVP. In fact, in that case, in that case, an infinite number of solution exist, right, because you can choose L equals to 1, L equals to 2, L equals to 3, whatever, n equals to 1, n equals to 2, n equals to 3, and so on. So your n is basically let us say a plus minus, I mean basically an integer. So then in that case you will have an infinite number of solutions in that case, right. And if L is equals to n pi and y1 is not equals to 0. So let us say y1 is equals to 1, say y1 is equals to 1, then there is no solution, of the boundary value problem, because we have 1 and then we have b and then we have sign what was it, L. So if L is n pi, then in that case sin n pi will be 0. So b into 0, that means 0. So 1 equals to 0. So this leads to a contradiction. So if y1 is non-zero, and if L is n pi, then in that case there will not be any solution, because we will run into an absurd situation, right. And therefore the only way that we can say that if L is equals to n pi and y1 is equals to 0, then in that case we will have infinite solution. But if L is equals to n pi and y1 is any non-zero number, then in that case we have no solution basically in this case. So this L equals to n pi will now define this eigenvalue definition. So this L is equals to n pi, sometimes it is denoted by lambda, and that is somehow called as the eigenvalue, right. So let me give you a formal definition. So eigenvalue problems associated with ordinary differential equation arise while considering physical problems like determining the displacement of a vibrating string. Vibrating this string, or determining temperature distribution, and so on. So any such type of physical problem. So the typical equation that often occurs in this problem is P1x. So this is the typical equation, y double dash x plus P2x y dash x plus P3x plus lambda into y is equals to 0, in which P1 and P2, P1, P2 and P3 are continuous functions of x in a closed interval AB, right, with P1x not equals to 0, obviously, otherwise it will become an ODE of order 1. So then the order will be reduced, so we do not want that. So P1x must not be 0. So and of course it will have the boundary conditions of this type. So A1 y at A plus A2 y dash at A equals to 0, and B1 y at B plus B2 y dash at B is also equals to 0, where a1, a2 and b1, b2 are all constants, but they are not zeros. For the time being, let us say that they are not zero. So, a1, a2 and b1, b2 they are all constants, and ai's and bi's they are not equals to 0. So, basically now let us name this equation. So, I am calling this as equation number 1 and this as equation number 2. So, now if there is a number, if there is a number lambda 0, and a function phi x such which is not identically 0, in a to b closed interval, such that the equation 1 and the boundary condition 2 are satisfied when lambda equals to lambda 0 and y is equals to phi x. Then lambda 0 is called the eigenvalue. And corresponding phi is called the eigenfunction. So, so basically this eigenvalue and eigenfunction, they are associated or related to the given boundary value problem. And since we have a second order ordinary differential equation, or most of the time we are dealing with second order ordinary differential equation, we cannot have more than 2 eigenfunctions. So, because for a second order ordinary differential equation we have 2 independent solutions, and therefore we will have 2 independent eigenfunctions. That means we will have 2 independent eigenvalues. And if phi 1 corresponds to, let us say, lambda 1 and phi 2 corresponds to, let us say, lambda 2, I mean phi 1 and phi 2 are the 2 eigenfunctions, then capital phi x equals to some constant c1 into phi 1 plus c2 into phi 2 would also be an eigenfunction corresponding to the solution, corresponding to the eigenvalues, basically let us say lambda 0. So, I mean we have phi 1 and phi 2, so of course their linear combination will become an eigen function as well, because phi 1 and phi 2 are already independent. So, their combination will be linearly dependent on phi 1 and phi 2. So, right. So, this is also an eigen function. So, in general, we can calculate the eigenvalue and eigenfunction of any second order linear differential equation. So, let us consider example 3, example 1, 2, 3, I guess. So, find the eigenvalues, and eigenfunctions of y double dash plus lambda y is equals to 0, which satisfies y at 0 equals to 0 and y at pi equals to 0, right. So, we have to find out the eigenvalues and eigenfunction of this equation y double dash plus lambda y equals to 0. So, here basically if lambda is 0, then in that case so we do not know the condition on lambda. So, if lambda is 0, then the general solution of the given equation is yx equals to c1 plus c2x, where c1 and c2 are arbitrary constants, where c1 and c2 are arbitrary constants. Okay. Now, if I use the boundary condition, that means if y at 0 equals to 0, then in that case I will have 0 C1 plus C2 into 0. So, this will become C1 equals to 0. And if I use y at pi equals to 0, so then I will have 0 C1 plus C2 pi. So, from here I will get C1 as 0, so C2 is also 0, and therefore, we can see that if you take lambda as 0, then both C1 and C2 is becoming 0. So, this implies that this leads to a trivial solution, that means y equals to 0 is the only solution. So, this leads to a trivial solution in the interval 0 to pi, but trivial solution is something that we do not want, because y is equals to 0 will always be a solution, but that is not something we should be analyzing or we should be looking. So, lambda equals to 0. So, lambda equals to 0 is not an eigenvalue, not an eigenvalue in 0 to pi. Okay, now let us say lambda is non-zero. So, if lambda is non-zero, then what will happen? If lambda is non-zero, then we have to check whether lambda is less than 0 or lambda is greater than 0. So, if lambda is less than 0, so let us say case 1, lambda is less than 0. So, if lambda is less than 0, then the solution in this case will be, what do we get? In this case, we will see that we will get yx equals to C1 e to the power minus of lambda square root of, and C2 into square root of minus of lambda x, right. Okay. Now, y at 0 equals to 0 is given. So, if I use y at 0 equals to 0, then I will get 0 C1, this is 1 and this is 1. So, C1 plus C2 equals to 0, and y at pi, right, y at pi equals to also 0. So, this will imply pi equals to C1 e to the power minus square root of lambda into pi plus C2 e to the power square root of minus lambda into pi. So, this equals to is it y at pi equals to 0, sorry. So, this is equals to 0. So, from here we will get C1, actually there is a negative sign here, sorry. So, there is a negative sign here. So, I will get C1. So, basically I am getting C1 plus C2 equals to 0 and C1 e to the power minus of lambda pi plus C2 into e to the power minus of square root of minus of lambda pi equals to 0. So, from here the determinant 1 e to the power lambda minus pi e to the power minus of square root of lambda pi. So, this will lead to we will have e to the power minus of square root of minus of lambda pi minus e to the power square root of minus of lambda pi, and this actually is a non-zero quantity. So, this is non-zero and this is non-zero, and therefore, we will have C1 and C2 equals to 0. That means, if the determinant is non-zero, then C1 and C2 must be 0, and therefore, this will imply that C1 and C2 must be 0, and this implies that y is equals to 0 is the only solution, right. So, even in this case, when lambda is less than 0, we are getting y equals to 0 as the only solution. We will look into the case when lambda is greater than 0 in our next class, and we will see that how our eigenvalues and eigenfunction look like. Alright. So, I stop here today, and we will continue with the same example in the next class, but we will start with the final case, that is when lambda is greater than 0. So, we will see that in the next class. Thank you for your attention.